How are NASA engineers using Fibonacci sequence and the golden ratio to research, design, and develop airplanes?
When NASA engineers are designing airplanes, they want to be sure that all their airplanes handle the same way. It's kind of like driving a car or a truck. Whatever car or truck you drive should perform the same way. Anyway, let's say engineers have designed a new airplane with a larger wing than a previous design. They have to use ratios to scale or size parts like the ailerons to fit the new wing. Ailerons are the movable parts of airplane wings that control roll. If the ailerons are not the correct size for the new wing size, the plane might not fly the way it should. So you see, the golden ratio helps designers determine the geometric relationships needed to keep the plane flying the same.
Hey guys, meet Bruce Holmes. He's an aeronautical engineer at NASA Langley Research Center in Hampton, Virginia. So Bruce, let us know what you're working on here at NASA.
Well, as Ardith told you, our transportation demand in this country will soar beyond supply in the new century, the 21st century. And we have just got to figure out how to make more places available to more people in less time. And so we're working with smaller airports and smaller aircraft that fly ever faster and ever safer than before to meet this 21st century demand.
You're telling me smaller airplanes? You mean like this smaller right here? How is that going to happen, Bruce?
Well, many people don't know that the ratio of the total number of airports in the country to the number that have hub and spoke airline service is about 10 to 1. And so we can go 10 times as many places and save time for people if we can figure out how to use these smaller airplanes in smaller airports. I mean, there are several ratios that aircraft designers use to sort of score themselves as the design of the airplane. Wing loading, for example, is where you take the whole weight of the airplane and divide by the wing area that you see out here. And that gives you a sense of the relationship between the weight of the vehicle to how much area is supporting it. Another ratio that's very useful is the total lift efficiency or lift capability of the wing divided by the weight of the airplane. And that tells you how efficient of a lifting device the airplane is, and it also tells you how long the runway needs to be because it tells you how slowly you can land the airplane. Very important ratio.
Okay, so I guess what you're saying is that smaller airplanes mean smaller runways.
Much smaller runways. You know, big runways at big airports can be 10,000 feet, 12,000 feet, 15,000 feet long. And yet you can use a runway that's only about 2,000 feet, about 1/5 the length.
Okay, Bruce, this plane already exists, obviously. I mean, you fly this thing around. How are you and how is NASA going to use an airplane like this to help travel in the future?
The Small Aircraft Transportation System, which is using smaller aircraft and smaller airports as a means by which we can move more people to more places.
And you're working on this right now at NASA.
What we want to do with SATs is make it possible for people to have another choice for intercity travel in the 21st century, a bypass around hub lock and a bypass around gridlock. If you want to be in those systems for other reasons, that's fine. We'd like to give people an alternative. We're proposing to make these smaller airports all across the country more accessible in virtually all weather conditions, with airplanes that are as easy to use as cars and cost about the same as a car trip for long trips.
And about as small as this?
Well, the airplanes will be a little bit bigger than this. I mean, you'll be surprised actually at how big they'll seem once you get in them. They'll seem more like minivans and things like that. So I mean, if you think about one of the other ratios or proportions that's interesting is how much power you have in the airplane relative to the weight of the airplane. We call it power loading, or thrust to weight ratio. And the people at NASA's Glenn Research Center are working on how to get more efficiency and more thrust out of less weight in engines.
This is like our little map here of telling us how to go. Let's plan a trip.
Are we there yet?
Gosh.
Well, here's how we find out. When you navigate, you pull out the map and you just kind of look at your route of flight, figure out where you're starting from, and where you want to go to, and this was kind of a big mess. I mean, you know, the more you got into it, kind of the more involved this whole thing became. Oh yeah, and then you peek over here and make sure everything's still going.
All right.
And we're going to put that away. Now it's all right here in the computer.
Oh, it's all right here?
Absolutely. So we can navigate, we can see where we are, we can see where the weather is, we can see where the traffic is. And we can see where we wanted to go, and we can also have all of the frequencies and all the information that was on that map is stored in the computer.
You don't even have to use the map.
Push a button and pull it up. That's the idea.
Wow, and you put all these technologies into this airplane.
This is an airplane that has many of the SATS technologies. There are many more to come, but this is sort of the grandfather of SATS airplane. So, Jennifer, Van, what do you say we button up and fly on over to the Research Triangle Institute and look at the computerized simulator where we can put some of this highway in the sky theory into action?
I love computers. Let's do it.
That sounds great. And you know, speaking of computers, did you know that the Boeing 777 was the first airplane ever to be designed completely using a computer? Isn't that right, Bruce?
That's right.
Yeah, they used computer technology, and it gave engineers immediate feedback and eliminated the need for building expensive models. So while Bruce, Van, and I head over to the Research Triangle Institute, why don't you go see Dr. Shelley Canwright and design an airplane using your own computer?